All right, guys, welcome back. I've had some question or someone wanted me to produce a video on different hole size calculations, specifically LSC, MCC, MIC, and MZC. So let's get into some of the basics of it. This is a massive subject, but we're just going to cover some basics. So if we just go to Google and search LSC, MCC, MIC, we come up with not a lot of information, but once we click into this, we'll find out. So let's go to this Science Direct. I've already got that one open. I don't know where it's at. Let's go to this. No, let's don't go to that one first. Let's go to this one. Nope, this one, which if you look is the Mitutoyo. So let's go to this one. So this is a page right out of Mitutoyo, which is this is a Mitutoyo CMM. And this will give you a little basic explanation. Just forget all this up here for right now. Let's look down here. This is all I can find from the Mitutoyo page. So it's talking about roundness tester. LSC, least square circle. So you can see a short description of it. Circles fitted to the measured profile such that the sum of the squares of the parts of the minimum profile data from the circle is minimum. Alright, so the roundness figure is then defined as the difference between the maximum deviation profile from this highest peak to the lowest valley. Minimum zone circles, MCZ. Two concentric circles are positioned to enclose the measured profile such that their radial difference is a minimum. Somewhat makes sense. MCC. Smallest circle that can enclose the measured profile is created. This circle is sometimes referred to as the ring gauge type circle. And hopefully if you're doing any metrology, you're somewhat familiar with a ring gauge, which is basically a precision gauge that slips over a diameter that gives you, like say if you're checking shaft diameters and you want to make sure that's right. Maximum inscribed circle, largest circle that can be enclosed. The roundness figure is then defined as the maximum deviation. The circle is sometimes referred to as a plug gauge. So if you're not sure what plug gauges are basically like a gauge pen that you use to stick inside of a board or ringed or sometimes even drilled or a honed hole into something. Plug gauges go in, ring gauges go over. Alright, so then let's look at, I clicked on ResearchGate and then I was able to download this. I think that's the right one. Anyway, the accuracy analysis of roundness test with a coordinate measure machine. All right. So, and I would definitely suggest that you would, if you're really wanting to learn a lot more than I can explain, download these documents. I'm just trying to hit the highlights. Calculated filling elements. Filling elements, least square circle, this one. Minimum and circumscribed circle, maximum and minimum zone circles. So I wanted to hit a few little highlights I've read going through this. The investigations prove that so-called minimum number of points 4. I've mentioned that in a video before. You need a minimum of 4 points, actually 3 points, to measure a circle, but as I've said before, I would definitely do more than 4, unless it's just a plus or minus 10 thousandths tolerance, and who really cares if it's that. If you're really trying to get accurate, you definitely need more points. So it says the so-called minimum number of points 4 is not enough for the circle measurement. It says it on the paper right here. So when the measuring points are placed, researchers, just software analysis. This right here says measuring points are placed on extreme points of the oval. The maximum MIC method may be placed in other disadvantageous It would be based on 3 points collected, which would affect the position of the center. So here you go. 4 points. You actually could throw your center off. Let's go down. Just looking. I'm just trying to hit the highlights. There's a lot of information that's really neat to read. I can't say that I understand everything. So differences between MCC and MIC are determined by the fitting element definition itself, while MCC and MIC methods describe the actual form of the detail. All right. Coordinate measuring machines as a conclusions. I'll jump to conclusions. Coordinate measuring machines are able to perform the measurement around this. The limitation is determined by the uncertainty of the coordinate measuring machine. Research described above have proved that the minimum number of measuring points for the circuits 4 is not enough and could generate sufficient differences in results. All right, here's all these references right here. All right, so then I jump to this one, I believe, Science Direct, and that one pulled up this one. Let me blow it up a little bit more. Circular feature and manufacturing environments. Methods of evaluating the roundness. So this one describes minimum zone circle, least square circle, maximum inside scribe circle, minimum circumscribed circle. All right. Look at this. Look at all the math that goes into this thing. Least square circles, there's the formula. It's got some different experiment demonstrations. Discussion and conclusion. Again, I'm jumping to conclusions. This paper introduced simple and efficient algorithms to evaluate the roundness error for measured points using 4 different methods. Among the 4 methods, only MCC complies with ISO standards. That's interesting. And has the minimum roundness error value. The LSC method is robust, but it does not guarantee the minimum zone solution specified in the standards. So, what is all of this telling us? Let's see if we can make some type of conclusion from it. Again, I am no expert in this. So, to me, it would depend upon why you're measuring the circle, what type of tolerance you have in it. So what I'm going to do now, I'm going to close this out, and I'm going to, I would highly suggest that you would look this up on your computer, bookmark it if you want to try to decipher more of this. I'm not going to. I just want to show you where they reach the information, and now we're going to go out to the machine and show how to pick different methods of doing this. It's Mitutoyo. Okay, so now that we went through all of that explanation, and I hope you got a vague idea of what all that is. So I'm here at the CMM. I don't have the video showing the table, but you can get the gist. All we're going to be doing is measuring a circle. So I've got my probe set up apart, and I want to go in here and measure a circle. I come up here and click circle, and so I'm looking for the LSC, MZC, MCC, or MIC. And wait a minute, where is it? Automatic, tolerance, graphics of measurement, all this stuff, minimum points for, sample circle, excuse me. Wait a minute, we've got mean, minimum circumscribed element, maximum inscribed element, minimum zone element. So wait a minute, what does this mean? This is not LSC, MZC, so how are we going to translate this? Well, for the sake of measuring, you remember in the previous section I said that 4 usually wouldn't cut it. I'm going to put 8 hits in here. And we're going to be measuring it at mean. Let's just go on and measure the circle. You won't be able to see this, but trust me. Took 8 hits, and we have, it says circle mean. Well, so after exhaustive study, and I still can't say I'm an expert at this, I have created a document that combines with the MCOSMOS manual on page 56, C1. MCOSMOS uses mean, enveloping element, fit element, and minimum zone element. At least that's what's in their instruction manual. So how do we translate least square circle, minimum zone circles, minimum subscribed circles, maximum inscribed circles? So I have conferred with some people smarter than I am about how does Mitutoyo, how does MCOSMOS convert this stuff. And it's not a true 100% conversion, but it's really close. And from what I understand, I have ran Starrett Apogee software in the past. I've ran the old Brown and Sharp validators back in the late 80s. I'll be honest, I didn't get into this stuff, the LSC, MCC back then, but we're here now. And from what I understand, talking with other people who have ran CMMs, nobody, well, I ain't gonna say nobody, most manufacturers of CMMs aren't super transparent as far as MIC, MCC. They have some method of doing it. I've been told that MCOSMOS is probably one of the most lacking as far as trying to figure out what this is. So I've created this sheet, least square circle. This is the MCOSMOS down here. This is a better explanation. So I made one document. So mean is an average of the element. This element is situated within the points, such a way the distances of single parts to both sides are roughly the same, more accuracy. So if you read through here, it kind of fits it. Roundness figures then define as the difference between the minimum. Minimum zone, let's go back to this. What is this one? Minimum subscribed element. See, that one's really that maximum inscribed element. Minimum, let's go to minimum zone element. All right, if we go back to our page, minimum zone element would be more or less in MCZ. Two concentric circles are positioned to enclose the measured profile such that the radial difference is a minimum. All right, a medium element that is situated in the middle of two ideal elements. So the minimum zone element would more closely align with the MCZ of minimum zone circles. Pretty close on their description. Now the next two, minimum and maximum subscribed circle, if you notice, the circle is sometimes referred to as a ring gauge. This one is sometimes referred to as a plug gauge. All right, so let's keep going. Enveloping element that calculates the ideal outer element by generating the smallest geometrically perfect feature that will encompass all the points. This is the largest geometric feature that will encompass them. That will only encompass the closest points. So let's go back to here. What is this? Oh, come on. Minimum circumscribed element and maximum inscribed. minimum circumscribed, which I didn't put that on the sheet. All right, let's go back to it one more time. Minimum circumscribed element. Minimum circumscribed element. Smallest circle that can enclose the measured per. So, ideal outer element, small geometrical, it will encompass. So anyway, enveloping element is MCC. I probably need to add this one to make it more fit. Minimum circumscribed. Hover, hover. Maximum inscribed. Right, this is the maximum deviation of profile. So this would be the maximum. This would be minimum. Maximum inscribed circle. Minimum circumscribed circle. All right, I put enveloping element and fit element, which is translated to here. But if you noticed, even the MCOSMOS documents don't truly show you this. Minimum circumscribed element, maximum inscribed element. So, this is a sheet I created, and I hope this helps you out. We could get into a lot deeper talk of minimum zone circles, least square circles, and how that a minimum zone circles could actually throw your true position out. If you've got some haywire, you know, like if you notice this one, if you notice from this circle to that circle, it actually will throw your true position out. Things like that can happen. And one last thing I want to show you is, let's do a roundness, a circularity, GD&T. We're going. So if we do a circularity, a GD&T circularity, it'll actually show our points where they were, minimum zone, tolerance zone. So it will graph out your points if you go in and do a circularity GD&T on the one whatever one you wanted it to. So you can kind of get an eye of seeing which one is out to however. So anyway, back to this. I hope this document will help you out. I will tell you again, I am not a certified quality engineer. I am a machinist that have used a CMM, and to my knowledge to date, this works, but I cannot 100% stamp and say, by golly, I know this is exactly right, because quite frankly, I'm just not that smart. So I hope all of this helps you out, and happy measuring.